So the reason I really want you to focus today is because the concept of ice tables isn't going anywhere for a couple months. So to save us, hopefully, a lot of meaning to review with you outside of class, let's be a little extra focused today. And I forgot something. I'll be right back.
No, it's not 0.053. Wait.
You said 0.058.
Oh, yes. So you do the NO squared, I think is about. No, you're solving for that, right? You're solving for NO squared. So you have the other one squared, which is 0.0768 squared. Take that, divide by 109. Divide that by 0.0159. Square root of that gives you the 0.003. You square root the 0.003.
Do I have any step-by-step
NO and it gives you NO squared.
way in your notepad to solve your equilibrium problems anywhere? Does it appear so? Okay.
Second coaching soccer.
For East? All right. So, I think we're pretty good. I'm not going to continue to ask the same question about equilibrium at this point. I'm hoping that we're all right. Here it says carbon monoxide reacts with steam to produce carbon dioxide and hydrogen. At 700 Kelvin, the equilibrium constant is 5.10. Calculate the equilibrium concentrations of all species. If you have 1 mole mixed in a 1 liter flask. Notice they didn't give us the equilibrium concentration of anything. Okay? Now, I gave you kind of a step-by-step process, and this is going to work for really most situations. I'm going to get rid of this out of the room. The first step, it says, is to do what?
To write the balance of chemical equation.
Okay? Sometimes they'll give it to you, sometimes they won't. Okay? If they don't give you the balanced chemical equation, you will need to write it. So what would it look like in this case?
No number needed, just CO minus plus H2O goes to
CO minus?
carbon monoxide wouldn't have a charge?
No.
No, it doesn't. No.
Plus?
H2O goes to produce CO2 plus H2. That's already balanced.
Okay, that's correct. And you can probably imagine why we need the balanced chemical equation. If we're doing the equilibrium expression stuff, we're doing anything dealing with equilibrium, we're going to need the correct balanced chemical equation. Okay, then what was, that's the first step. What's the second step? And you might already have guessed it, but what does it say? Okay, I'm going to write the equilibrium expression. So, and we know what K is in this context. What is it? 5.10. Give it to it. It gave it to us. Products over reactants, which you guys are familiar with. Everything's a nice 1-to-1 ratio, so this is going to be the easiest form of this. We will get into not 1-to-1 ratios where it will get a little bit more difficult. Step 2, done. Okay? Whenever we're doing equilibrium stuff, that should be a no-brainer that those are your first two steps. Equation's got to happen because you have to be able to write your equilibrium expression, and then once you have your equation, write your equilibrium expression. I mean, we're doing equilibrium problems. Now what? Why would I need to calculate Q?
You can tell we need to go right or left.
Yeah, because part of being able to figure out the concentrations of equilibrium is going to have to do with whether or not I'm going to produce more products or whether or not I produce more reactants to get there. Because that's going to determine if I add or subtract. So, step 3. Q equals, I'm going to plug in the initial concentrations or the concentrations they gave us. What are the concentrations that they gave us?
1 mole each.
1 mole in. Nice. So what's Q? Now, the purpose of finding Q is to see, one, if I'm at equilibrium, and if not, which way I'm going to shift. So can you guys remember which direction this guy is going to shift then, if Q is less than K?
Right.
So shift right. All right. Nothing up to this point is new, is it? Okay. Step number 4 is where we begin writing our ice table. And I should have written this equation lower. I'm going to rewrite the equation here. Just so it's closer to where I'm going to write my ice table. Okay, so I'm going to start my ice table here. I, C, E. And actually,
Just 1 for everything,
I'm just going to write kind of what they represent. Is our I represents our initial concentrations, our C represents our change in our concentration to get to equilibrium, and our E represents our equilibrium concentrations. Am I going too fast for you guys?
This
Erase
part,
much
yeah,
of that?
this is the part Steve kind of helped me with even.
What?
This is the part Steve kind of helped me with on Thursday.
Really?
Yeah.
Okay.
So we got this so far. Write the initial and then.
So we already know the initials for all of them. And now will they all be 1? It depends on the situation. Very rarely, a lot of times they'll give you only reactants and no products. Sometimes we'll talk when we get into acids and bases where if you have a salt already in solution, you'll have some product. Okay, we're gonna get into a whole variety of things over the course of the next couple months. Okay? Just kind of laying the foundation of what the ice table is. I don't want you to just mindlessly do this. I want you to have an idea of what's going on here. So I know everything's a 1 molar start point. But I think step 5. So technically, this ice table would be like step 4 through 6, I think. Well, it's actually kind of 4 through 5. We'll say 4 through 5. You use the ice table 4, 6, but okay. Next, we have to identify the change that's going to occur with the variable x. What I mean by that is I want to know, as this progresses to the right, am I gaining products? Am I losing products? Am I gaining reactants? Am I losing reactants? What's the relationship here?
You're losing reactants, gaining products.
Okay, and that is why this is important. Because if it's shift left, you're going to gain reactants and lose products. Does that make sense? So, because I'm shifting right, I'm going to be losing my reactants. And the reason why it's just x and not 2x or 3x or 4x is because of what? Coefficients. Everybody got that? So then what is my product change going to be? What is it? Okay. Now the E, or the equilibrium concentrations, are going to be the initial and your change. So I started with 1 molar, and I'm going to subtract x from it, because isn't that how I would get my equilibrium? Whatever the change is from what I started with should give me my equilibrium concentration, correct? Looks like that. Alright, so that should be 4 and 5. And 6, it says substitute the equilibrium concentrations in to the equilibrium expression and solve. So, this is the mathematical equation that represents what the equilibrium expression is, or what the equilibrium concentrations are going to be. And since we know the constant, we can substitute those in and solve. So it should be step 6. 5.1. Products over reactants. So because it's 1 plus x for both, I can go 1 plus x, whoopsies, squared, does that make sense? All over 1 minus x squared. Whoops. Everybody understand what I just did?
Yeah.
I basically just substituted into the equilibrium expression what the mathematical relationship for those equilibrium concentrations were. Okay, I'm going to step 7. Or 6 is still actually says solve, right? So we got to solve yet? Okay. What are we going to do here?
Square root of both sides.
Square root of both sides, get rid of the square?
Yeah.
What's the square root of 5.1?
2.258.
Okay, 2.258
31798.
equals 1 plus x over
No. 1. Oh, yeah.
1 minus x, correct?
Yeah.
Can you guys solve for x, or you want me to go through this all? I'm technically not showing kind of the work here, but I'm hoping you'll be able to figure out that I took this square root there, right? Okay, I'm going to multiply 1 minus x over. Distribute through. And do 8th grade math. Stop me if I'm going too slow. Or stop me if I'm going too fast, I should say. Everybody see what I did there? Now I'm going to do the next thing I'm going to show you. I'm going to kind of do 2 things at once here. I'm going to move this over here to make it a positive x, and I'm going to subtract 1 over here in the same same step. So if I subtract 1, what does x equal?
Where did the X go?
Where did the other x go? I added it over here, brought them together, did that.
Okay, right, okay, great, yeah.
What'd you say?
I've done this in a while.
Okay. So, what does that tell us? What's x? What?
What's the change?
It's a change. So, okay, so it doesn't say what it, so in 7 it's saying once you know what the equilibrium concentrations are, plug them back in and make sure that they equal the K that you were given. That's just a way to check to see if you did it right. But to figure out what my equilibrium concentrations are, is we said this is the relationship of my equilibrium concentration. So I'm going to plug x back in and figure out what my equilibrium concentrations are. Does that make sense? So the concentration of CO is going to be 1 minus 0.386. Actually, I'm going to go, I'll just get rid of them all. Same thing for my water. And then my two products, I'm adding. And this should make sense since it's a nice simple 1-to-1 ratio, that what I lost on the reactants would be what I would gain with the products. Okay, what, 0.614? Look right?
61387.
Point, or 1.386.
If there are no coefficients become exponents, all of the reactants will be the same as other reactants, and all the product will be the same as the other product.
Sure, yeah.
Unless the beginning will ever be different starting.
But yes, they could have different starting
Well,
points.
like,
Yep.
the react-
So yeah, I wouldn't make that.
Okay,
That's that's assuming a lot of this.
okay. So
The process is the same, but are you going to see these two the same and these two the same every time?
Right, but the
Very
C would be,
rarely.
if there's no exponents, the C would always be the same.
Yes,
If there's no exponents, the whole thing, okay.
your change would be the same, but if you had different starting
Right.
concentrations, your equilibrium concentrations would be the same.
Great.
Now, what 7 is saying is you could take these numbers, plug them back into here, and make sure that you got 5.1 as a way of checking to see if your work is correct. I don't know what
5.0985.
Yeah, that seems like wrong number.
Same with number 3.
Yeah, you could probably put an extra 8. I'm not sure why that's there. Off the top of my head. Questions on this?
How do you use this to solve for calculate the equilibrium concentration of all species? Oh, we did that. Great.
Yep, that's what this is.
Yes, yes.
Concentration, equilibrium concentrations of everything involved.
Okay.
Any other questions?
That's the E is kind of your answer.
Yeah, after you plug back in. Yep.
So
Yeah.
the reactants will always have the same sign and the products will always have the same sign for the X?
Yes, but these could both be plus,
Yeah.
these could both be negative if it were shift left.
And it could be like 2.
Yes, like if this was a 2 here, then this would be a minus 2x, in which we'll get to one that has not a 1-to-1 ratio for everything here. How did you get that?
It's the 1.386 squared over 0.614 squared. That's all I did.
Alright, this next one, how much of this do you want me to go through? And how much of this do you want me to let you work on? What's your thoughts?
Everything up until the ice.
You can do everything up until the ice table? What do you guys think about that?
I probably control it.
So you're gonna, okay,
My,
at least do 1 through 3. Get your equation, balance it, write your equilibrium expression, figure out which direction it will shift, and then we can probably hit the ice table. And actually, I think the stuff right here today isn't too bad. It will get harder. We will see the quadratic equation, which is, I guess, you know, still freshman math, I guess. But is it all right if I start writing some stuff up here? You can check and make sure you're following it right here. Got that so far? Still working?
For E, would be 2 plus 2x. If it's x at an exponent.
Say that again?
For E, it would be like E minus x plus 2x. Would it be 2 minus x? And then that's the.
You're talking about for equilibrium?
Yeah. It would be 2.
It's always your initial and your change.
So it's 2 plus 2x. Great.
You would always want your starting initial concentrations and then what your change would be to get to your equilibrium. Have we figured out which way it's going to shift? Shift what? Shift right, okay? And you have your ice table, our initial concentrations go in first. which it was 2 molar for everyone, right? Yep. Since it shifts right, gaining or losing reactants?
Gaining products, so losing reactants.
Everybody see what I did up here for this change? A little bit different than what we did last problem. Our change for the product in this situation is going to be 2x. This should make sense. I'm going to react these reactants, but I'm going to produce twice as many products based on the coefficients. So my change should be twice that of my reactants. Then your equilibrium will be your initial and your change. Good? Anybody not following? Griffin Brothers, you with us? Oops. That's awkward. It's okay.
I don't understand on Q how it's 2.
This?
That's what I was thinking.
What?
I figured you wanted to be parents already in psychology.
What's your question?
Why is it 2 and not Q?
Why are these both two? It says 3 moles of each component is added to the 1.5 meters. So to get molarity, moles divided by volume.
Then I used to say that all the time.
What, that made me mad?
No, during psychology, you used to like make that joke or say that all the time.
What? This is awkward?
Yeah, one time Matt walked into that class towards the end. We were just going a few minutes late. He walked in, kind of went, "Whoa, this is awkward."
Matt did
Why
that?
is this up?
Yeah,
Who was in there?
psychology
We
class.
were just.
We're in the university room.
Oh, he just thought it was awkward.
Well,
that
it's
you
study
guys were
hall,
there?
8th hour. We had a 7th hour. And we were running a few minutes late.
Oh.
He didn't realize we had a class 7th hour in there.
Oh, okay.
Yeah.
Anyways, now we're going to plug into our equilibrium expression. Don't forget that we have our product is squared. And actually, this becomes still pretty easy math because we have both of them squared. Because I started with the same initial concentration, so it ends up being 2 minus x times 2 minus x, which would be 2 minus x squared. If these were both not squared, guys, you would have to use probably the quadratic equation. But since they're both squared, you can take the square root and get rid of the square. Square root of 115 is
10.72.
Try to go a little bit more than conventional.
10.72380529.
Well, no, that's a little over conventional. The reason why I say this is because there's enough math involved here that if you round too much, you could very well get an answer that's significantly off. That make sense? Okay, and then solve for x.
1.52.
53. I'll let you guys solve for x and make sure you get 1 point. Technically 528, probably.
Yeah, 528.
Everybody able to get 1.528?
Okay, I get that.
Y'all gooby? Everybody? Yeah? So, we stuck with some of the simpler math stuff today. We will, like I said, we'll get into a little bit trickier math, but the whole process is gonna look very similar to what we just did today. So, I don't know how many homework problems I gave you today.